Hey everyone, my name is Mickey Boxell, and I'm a product manager at Oracle responsible for our managed Kubernetes platform, OKE. Today, I'll be presenting with Rishi Sampath, a senior principal architect from A10 Networks. Today, we're going to be discussing building beyond Kubernetes, the tools and services that complement Kubernetes to form a complete cloud-native environment. Also, before we get started, I wanted to remind you that during the presentation, we want to hear from you. So feel free to ask any questions in the Q&A chat at any time, and we'll have an expert on standby ready to answer your questions. Also, if time allows, we'll have some time to answer some questions live at the end of the session. To begin with, take a sec to review our safe harbor statement, and then we'll dive right in. So our agenda for the presentation today is as follows. I'll be starting off by sharing an example cloud-native use case and continue to reference it throughout the presentation. Next, we'll make sure we're all on the same page about key concepts such as containers and Kubernetes. After that, we'll dive into what we mean by beyond Kubernetes, including a number of demos. This includes discussing package management and CI/CD pipelines, observability and service mesh, serverless functions, and all of the associated services and tools. After talking about the role beyond Kubernetes, we'll hear from A10 Networks, a company that has already made the leap from cloud native. Finally, we'll wrap up with some recap and some key takeaways. To understanding adopting cloud-native technology, it can help to have a real, and in this case, real-ish world use case. With that in mind, I present the company MuShop. MuShop is an e-commerce company focusing on pet-related retail. MuShop recently started their cloud journey by lifting and shifting their e-commerce platform to the cloud, but they haven't rewritten their application to take advantage of cloud features, such as pay-per-use elastic resource pools. I chose this example because many companies find themselves in a similar situation and want to figure out the best way to modernize and improve their application. While MuShop isn't a real company, it is a real open source implementation of an e-commerce platform built as a set of microservices. It's also designed to highlight cloud-native best practices, many of which we're going to discuss today. Additionally, it showcases a number of Oracle Cloud Infrastructure services in a unified reference app. A simplified version of this app can be deployed yourself using just the free tier of Oracle Cloud. A more advanced version can be deployed using the full version. You're welcome to navigate to the IP address at the bottom of the page here, the 193 address, and play around the app yourself, or go to the link at the top of the page and follow the steps to implement it. I'm going to navigate there myself in just a moment to show you what it looks like. But before I do, I'd like to draw attention to the architecture diagram here. We can see this is a microservice app broken down by business function. For example, the product catalog is in one set of containers, while the customer-facing storefront is in another. Also, it's worth noticing that this app is a polyglot application. It's written in Java, Go, TypeScript, and a couple of other languages. And it's connected to a number of Oracle Cloud services, such as Autonomous Transaction Processing, or ATP, object storage, streaming, Oracle Functions, and even more than just that. All right, let me switch over really quickly to show you what that application looks like. So to begin with, we have our reference guide here, the Oracle Quick Start. So if you'd like to implement this yourself, you can do that by navigating to this page. I'll also have all of these links shared later on. Next, I'm going to show you the application itself. So this is what MuShop looks like. You can see right here, it's deployed at a public-facing IP address, which is managed by a load balancer that's connected to my Kubernetes environment deployed on Oracle Cloud. So this is the example application. As you can see, it's everything that your pet could possibly want. We have a catalog of services, including feeders, food. You can add these to a cart if you want to. And as I mentioned before, all these different components, the upfront shop, the customer-facing splash page, and the cart and the ability to check out the cart, the registration system. Let me create a quick account right here. All of these are different microservices. And so what's cool here is that we can see, based on the architecture diagram that we saw before, that all these microservices are working together for a unified feel. So the version of the app we're looking at right now, you can imagine, is effectively the ultimate version deployed in a cloud-native way. And after jumping through this really quickly, I'm going to save my info, add a fake payment method, and then finally jump back in just so you can look like what it looks like on the back end. Cool. So we've entered some fake information here, and we're going to place our order. And once again, just keep this in mind when we continue talking about MuShop throughout the rest of the presentation. So after deciding to adopt a cloud-native approach, MuShop wasn't sure exactly where to begin. They found a white paper published by Oracle entitled Cloud Native for the Enterprise, which followed the Cloud Native Computing Foundation's Cloud Native Trail Map. I have links to both on this page. This strategy proposes a stages of adoption at a pace that allows teams to develop the skills they need. The nice thing is that means they don't have to jump into the deep end of cloud native right away. It means that each step along the journey just comes in the form of adopting more complex software to deliver cloud native apps. MuShop looked at this approach, decided that it was close to right for them, but they wanted to follow a modified version. And that's the version we're going to talk about today. For those who are already familiar with Docker and containers, don't worry, this is just meant as a quick level set for those who aren't. MuShop began their journey by deploying their monolith into a container. Containers allowed MuShop to bundle software with its runtime configuration and dependencies into a package. The functionality using namespaces, C groups, and other tools to isolate workloads has existed for a long time in the Linux world, but it only recently became popular after Docker simplified the process using easy APIs and tooling. Any place that has a Docker engine can now run the package or application in the same way, which means that everything is fully portable. Containers really facilitated a switch from monolithic applications to microservice ones. This came with a number of benefits, including faster development cycles, quicker time to market, and the ability to write components of the application using different languages. As we saw before, MuShop has a polyglot application now, and this was only made possible via microservices. After beginning by deploying their monolith into a container, MuShop started to decompose it into a set of microservices, each of which runs as its own container. But after decomposing their application and packaging it into containers, MuShop found that they'd accidentally created a huge problem for their operations team responsible for keeping it healthy. They had so many different bits and pieces and had no idea how all of them were connected, and it was very difficult to pinpoint issues. This led to a need for a system to ensure that many components of their app were properly networked, highly available, scalable, essentially a platform to make sure everything kept running and kept up with demands on the service. And this is where an orchestrator like Kubernetes came into play. Kubernetes is an open source system for automating deployment, scaling, and management of containerized apps, and it allowed MuShop to deploy their containers to a cluster of nodes and manage them at scale. Most of the heavy lifting related to container operations was done for them. Kubernetes allowed them to group containers into pods, which are co-located and share resources. They could further group together those pods using deployments, which represent a scalable application unit in their cluster, and then schedule that work onto a set of infrastructure nodes. They also use the Kubernetes concept of a service, which is responsible for enabling network access to a set of pods. Kubernetes effectively gives pods their own IP address and a single DNS name for a set of pods and can load balance across them. But as you may be able to tell from that brief description, Kubernetes is a pretty complicated tool in its own right, and managing that platform ended up being too time-consuming and costly for MuShop. There's a reason that the white paper describing the way of configuring Kubernetes is called Kubernetes the Hard Way. So MuShop decided to instead go with the managed version of Kubernetes, in their case, Oracle Container Engine for Kubernetes, or OKE, which gave them the control they needed while also offloading the management of the platform itself. Managed Kubernetes solutions contain tools to help create, scale, manage, and customize Kubernetes clusters, and also take advantage of the tightly coupled underlying infrastructure of the cloud provider. They're also built to integrate with related tools such as image registries like the OCI registry service, which are used to store container images. I'm going to quickly pop over to the Oracle console to show how easy it is to create a cluster, and also what it looks like with MuShop's application deployed on a Kubernetes environment. So right now I'm in the Oracle Cloud Console. I'm going to jump over to the Developer Services section, which is where I can find Kubernetes clusters. And I'm going to walk through the process of creating a quick create cluster. So creating a cluster can be done in just a couple of clicks. You have the option to create a custom cluster, but also the option to just pick a bunch of defaults and begin with quick create. Quick create really simplifies the process of creating a cluster. I'll select the quick create radial button and then go through the process of picking a name for my cluster, such as example, choosing the Kubernetes version, choosing the visibility type for my nodes, either private or public, choosing a shape to underlie my nodes, and then also specifying the number of nodes and a couple of other options such as custom boot volume size. All I do next is click next and then review my choices and then click create cluster. And within the next few minutes, I'll have a Kubernetes cluster up and running and ready to go. I didn't have to mess around with deploying etcd or any of these other complicated cluster components. I can just very simply close this, wait for my cluster to come up, and then start deploying applications. The next step is to show you what it actually looks like after MuShop deploys this application to a Kubernetes cluster. So I'll click into the MuShop cluster. I can go to the node pools in the cluster, which are simply just worker nodes or virtual machines where work is being scheduled. And I can see that in this case, it is highly available. I have 3 nodes spread across 3 different availability domains within a data center. And then the next step is I'm going to actually connect to the cluster itself. So I'll click Access Cluster. We have a very simplified method of doing that via Cloud Shell. I'll use kubectl, which is the command line tool to interact with Kubernetes. Doing this, we can see that same set of nodes that we saw on the previous page, simply just 3 nodes spread across availability domains. Then I can see all of my containers grouped together in pods, which are deployed on the MuShop namespace within Kubernetes. If I expand this more, you can see that I have each one of those deployed as microservices. In some case, each pod has multiple containers running within it. And this is our highly distributed microservice-based application. So while containerizing their application and deploying it to a managed Kubernetes platform addressed many of their initial motivations to adopt a cloud-native approach, MuShop found that there were still things Kubernetes alone couldn't accomplish. They decided to focus on a handful of these gaps and tackle them one at a time. The gaps included a need to repeatedly deploy groups of containers and also the ability to take advantage of automated pipelines to assist with building, testing, and delivering containers. They also wanted to be able to monitor their workloads. As we discussed before, microservices come with new operational challenges, so they needed to be able to pinpoint and resolve issues that might take place in the cluster. And they also needed to simply deploy business logic connected to the platform without worrying about the underlying infrastructure. Fortunately for MuShop, they discovered that while they had the option to build these tools on their own, just like they had the option to deploy Kubernetes on its own, there were already a number of solutions available for them. Many of the gaps could be addressed by means of managed services. For example, in addition to being able to manage a Kubernetes environment and a container registry, Oracle also offered tools to help manage APIs, monitor workloads, and add additional functionality through serverless functions. It also provides the ability to provision a number of other cloud services that are commonly used to support cloud-native apps, such as streams or databases. And in addition to those tools, Oracle also partnered with a number of other providers and added support for a variety of open source projects to further fill in the gaps. You can see some of those here. These tools can be either managed or unmanaged, deployed on your own, or relying on another provider. And I'm going to talk about a few of them as we revisit those initial expectations from MuShop. The first gap MuShop sought to address was package management, which is simply the ability to wrap up a group of containers and related settings in Kubernetes into a logical app that can be repeatedly deployed, versioned, and rolled back. MuShop chose the tool Helm, which calls itself a package manager for Kubernetes. And especially after changes made in the most recent release of Helm, Helm became an industry standard for this sort of deployment and comes with a bunch of helpful repositories of templates for deploying applications. Many of the projects we'll talk about here today are actually available via Helm charts. MuShop packaged their containers and configurations into Helm charts, and you can see this yourself when you check out the project. By adopting Helm charts, they're able to more easily deploy, update, and version their application. Next up was, after solving the packaging issue, MuShop wanted to take advantage of the automated pipelines to assist with building, testing, and deploying containers. The shift to microservices allowed them to iterate each component of their application independently, which in turn sped up development velocity. While this was a great benefit for them, it also forced them to address a new need for automating the testing process. MuShop chose GitLab as their underlying DevOps platform and connected the tool to their Kubernetes cluster and container registry. In their system, developers check new code into a repository using Git for source code management. This would be the continuous integration part. Each code check triggers a build process, for example, Maven or Gradle for a Java application. And after the build process is completed, assets are generated and tested. The code is packaged into one or more containers using Docker tools, and also Helm charts are created as well. Newly generated container files are pushed to a registry so they can be downloaded when needed. And this registry can be a public location, for example, Docker Hub, or a service like the Oracle Cloud Infrastructure Registry service we talked about before. Next up, the container or containers are deployed to an orchestrator such as Kubernetes. And because the process is automated, MuShop can expect the same behavior anytime they check code in. And if there's ever a failure, they can very simply just roll back to the previous iteration. MuShop also wanted to make sure they had tools and an ideology in place to address potential issues in their system. They chose to adopt principles of observability. And when I say observability, I'm referring to designing and operating a more visible system. Observable systems are systems that can explain themselves without the need to deploy new code. These types of systems, especially complex distributed ones, will inevitably experience failures, and it becomes important to recognize and prepare for those failures. The observability philosophy differentiates itself from system monitoring because observability takes a more holistic approach that includes proactive systems and process design. This includes not only the ability to test an environment in a realistic manner, but also the ability to report useful, actionable data in production and considerations for business impact. There's no longer such a notion of just an IT issue, but also the impact that has downstream to your business. Monitoring provides users the ability to determine the internal state of a system through external outputs. And those outputs are usually logs, metrics, and traces. Combined, these three pillars are used to accurately and quickly triage adverse events to restore normal service. They can also help you conduct a useful postmortem to help avoid similar events in the future. Unfortunately, Kubernetes doesn't include much in the way of monitoring how software deployed in the cluster behaves at runtime. And for that reason, MuShop had to rely on some additional tools. Logs, which are considered to be the most fundamental pillar of observability, are a record of an event that took place at a given time, consisting of granular info for a specific context that can be used for diagnosing problems. Logging is supported by almost every library I can think of, but it's just important to remember to be disciplined to put meaningful logs into your code. It's also important to remember to implement a tool to aggregate logs, or else they can become lost. And this is especially true in an ephemeral containerized environment. MuShop chose to implement the open source log forward of FluentD, which allowed them to scrape logs from all the nodes in their cluster and process and ship them to a persistent data store, which in their case was Elasticsearch. Elasticsearch is an open source analytics engine which can be queried directly or interacted to by means of Kibana, which is just a visualization dashboard. These three comprise the so-called EFK stack, which is a great tool for centralized cluster level logging and the tools needed to analyze those logs. At the end of the day, there are other tools you can use, but it's just important to remember to choose a tool that captures logs and provides you with the ability to accurately sift through the data they provide. The next step was figuring out how to capture metrics. Metrics are a numeric aggregation of data describing behavior of a component or service over time. Because they're numerical rather than text-based, they're super good for storing and modeling data. And this means they're also useful for understanding typical system behavior. In the Kubernetes space, there are metrics available on so many different levels, from the underlying nodes to the cluster components, to your application pods, to the performance of an application itself, for instance, requests per second, error rates. The good thing is that most application frameworks include libraries to instrument metrics. MuShop chose to use Prometheus, which is just an open source system monitoring toolkit that included libraries to create and process samples, tools to scrape data, and also the ability to send that data to the Prometheus time series database, in addition to a query language to analyze the data. They paired Prometheus with Grafana, which is an open source visualization tool, to help create helpful dashboards and alerts from a variety of data sources. They also used the Oracle Cloud Monitoring Service, which offered out-of-the-box metrics for OCI resources. One cool thing is that Oracle worked with Grafana to expose that monitoring service data as a Grafana data source, which meant that MuShop could visualize Oracle's cloud infrastructure data alongside Kubernetes data and other data sources in one unified visualization. So now let's take a look at their environment and the OCI monitoring service along with Grafana. So the first step here is I'm going to jump into what it looks like to use OCI monitoring. So I can see right here, I'm on my cluster page, and if I scroll down, I can see some basic data related to API server requests, server responses, and unschedulable pods. If I jump into the node pool, I can see data about the nodes themselves, including node state and Kubernetes node condition. So these are just some of the metrics that are available out of the box with the OCI monitoring service. If I go to my Grafana dashboard, I can see even more. In this case, I deployed Grafana using Istio, which is a service mesh I'll talk about later. And I can see some of the data about Istio. So for instance, the performance of the mesh itself. And then, as I mentioned before, because there's a lot of information on multiple levels, I can also see data related to my Kubernetes cluster. For example, pod usage, CPU usage, memory usage, etc. More advanced users will have this connected to the different applications running within their cluster. But it's just important to note that within Grafana, you can see a lot of data from a variety of sources aggregated in the same place. Now, the final pillar of observability is traces. Traces represent causally related events that are part of a request flow in a distributed environment. They are uniquely suited to understanding the entire lifecycle of a request because they provide visibility into the structure of the request and the path that it took. As a result, they're very useful for pinpointing issues, for instance, increased latency in a system or increased resource utilization. They're also helpful for debugging. Tracers live in your application code, and the way they work is by assigning each request a global ID and then inserting metadata at each step in the flow. This is referred to as a span before passing along the ID to the next step in the flow. One challenge of tracing is that it can be hard to retrofit existing apps to support it. Each component of an app needs to be instrumented to propagate tracing info, which is especially challenging in a polyglot architecture. MuShop took advantage of the Open Tracing API, which is a language-neutral approach to distributed tracing, which worked well with their polyglot environment. They chose to visualize traces using the open source tool Jaeger. Another option I looked into is Zipkin. Fortunately, those are both cross-compatible and also both supported by service meshes. Now, the next step for MuShop was introducing better control over how different services in their cluster interacted with one another. To accomplish this, they turned to the Istio service mesh. Service meshes, in a nutshell, are just an additional layer of functionality that offers more sophisticated control over the connections across services. They provide a configurable infrastructure layer for microservice applications. They're often used to monitor and control the flow of traffic through services deployed in a cluster. They're typically associated with Kubernetes because they work so well with microservices. Many service meshes use a sidecar pattern, which is just the practice of provisioning each pod with a proxy container, usually Envoy, which controls and mediates network traffic between services in the mesh and doesn't require any code changes. Istio has the added benefit of out-of-the-box integration with the tools we just talked about, including Grafana, Prometheus, Jaeger, and Kiali, which I'll show shortly. And those are all tools MuShop was already using. It also pre-populates those tools with helpful dashboards, so you have some sensible defaults to start with when you get started. The service mesh pattern, in essence, provides, in addition to traffic control, observability and awareness of what's running. So let's see what MuShop service looks like when it's deployed with the service mesh. So right now we're looking at that mesh visualization tool, Kiali. Within here, I can see the different namespaces in my Kubernetes cluster: default, Istio system, MuShop, MuShop setup. If I jump into MuShop, I can go to show applications to show all of the different components of this application: API, assets, carts. All these are different microservices deployed as containers in my cluster. If I were to pick one, for example, storefront, I can see the health status of the pod and also some recent requests. So let's see, if I had any traffic on here, I could start seeing some traffic related to each of the requests going through the application. In this case, it also shows me request type. So in this case, it's HTTP, but it also could be gRPC or other protocols. Now, where I really see the value of Kiali is in these visualizations to see how everything actually interacts. So previously, we saw half a dozen different microservices all interacting with one another, but we couldn't really see any sort of causal relationships. In this case, we can actually see how those different components are related to one another in a visual and very easy to understand graph. The last bit I want to show is serverless. So as we mentioned before, MuShop wanted to add some additional functionality to their service without needing to manage the platform underneath. Serverless is a further abstraction of the cloud. With containers and Kubernetes, we're decoupled from the host environment and we can worry less about infrastructure. With serverless, we can abstract even that away and focus only on business logic. What people refer to as serverless, of course, does require servers somewhere, but they're not something the end user directly interacts with. Oracle Functions, which is our serverless implementation, is integrated with Cloud Events, an industry standard event exchange format that tracks user-initiated, system, and also resource lifecycle changes. MuShop's last step was to add a newsletter subscription to their service, and they did so by means of a function, an API gateway, an event, and the email delivery service. When a customer uses the subscribe button on the console and passes through an address, it hits the subscription API endpoint, which triggers a function, which then sends out an email confirming their subscription. We can also imagine that the customer contact is passed through to a database in the backend. By using a function connected to the service managed by a cloud provider, MuShop avoided having to set up their own SMTP server and other always-on resources. They pay only for the execution time for their function to complete. People often ask about appropriate use cases for functions. I included some of the common ones here. But really you can do most of anything. Some simple ones like event-driven governance Or when resources are created, you can make sure they follow your corporate policies. But really anything can be created with the function. I've even seen someone create the game Doom using serverless functions. Maybe not the best UI, but still a fun exercise. And now that we've run through the last bit of MuShop's requirements, I'd like to turn it over to Rishi from A10 Networks to hear about his company's use of cloud-native services.
Hi, everyone. So A10 uses OCI in multiple ways to enrich its offerings. At A10, we serve the most demanding service provider and enterprise customers. Our solutions are capable of supporting hundreds of millions of concurrent sessions while delivering high performance and high reliability. We found OCI to be very performant and functional, making it very compelling for us. We consume OCI services in 3 flavors. The first flavor is where we have a SaaS-based management system called Harmony Controller. There are aspects of the solution that demand massive scale and performance. One, we store logs and associated metrics for all the traffic passing through our offerings. And as we keep increasing our product footprint, these demands keep growing. The Harmony Controller was built from the grounds up as a cloud-native multi-tenant offering. It is a microservices-based architecture comprising of 20+ services. We leverage some of the capabilities of OCI, especially their observability smarts, block storage, and other services like DNS. Orthogonally, as part of our testing, staging, and deploy cycle, we also run a Jenkins job. So on a successful build of either microservice or the entire solution, we trigger and launch an exhaustive sanity test that runs for hours or days, and after which we tear down the entire setup. Here, we make use of OCI's Terraform provider to spin up the entire testbed and associated test tools. So OCI has been a great partner, a great cloud on which to basically run a Harmony controller, which offers seemingly infinite storage and scale. And couple that with massive, excellent performance. This was what made a great cloud on which we could host a Harmony controller. Next page. The other way we consume OCI is for running our complete regression test suite against our products. As I mentioned before, A10 products are deployed in the most demanding service provider and enterprise customers. We have a massive test bed running our regression test suites. Our regression infrastructure qualifies any of our 4 product lines in hours, validating entire capabilities across the entire network stack. So this was an opportunistic lift and shift operation for us. We looked at the OCI Terraform provider implementation and found it to be very comprehensive and evolved. Using OCI's Terraform provider, we could seamlessly create a complete automation topology with hundreds of nodes and parallel test beds on OCI. And based on demand, we could just scale this infinitely. Thus, we could lift and shift an entire homegrown test suite that qualifies our entire application delivery product lines, which power the most demanding service provider enterprises. Next page. The third way we consume OCI is using Oracle Cloud's My Services API. We use the service discovery smarts from the service engine to query the health of nodes where application workloads are deployed in order to ensure application delivery. This is because as a workload scales on multiple nodes or shrinks or is redeployed, we need to dynamically figure out where the workload resides. The other aspect of OCI which makes it particularly impressive are its failover times. We use it internally in our product lines to provide failovers across availability domains within a region. So A10 has been a very happy customer of OCI. We consume it in multiple ways, and what has impressed us has been its particularly its performance and failover capabilities. Thanks, Mickey.
Thanks, Rishi. Appreciate it. And I hope we have some good questions for you after the presentation's done. Now I just want to recap the journey that MuShop went through to reach their current cloud native state. They began by containerizing their application. Next, they decomposed it into a bunch of independent microservices that collaborate together to provide the required functionality. They ran their application on a Kubernetes orchestration platform and noticed some gaps. So they figured out some services and tools that could come into play to fill those gaps. They packaged their components of their application into a bundle using Helm. They set up a CI/CD pipeline using GitLab. They instrumented their application with logs, metrics, traces for observability using a combination of tools. They wired everything together using a service mesh for sophisticated horizontal traffic control. And finally, added some additional functionality using Serverless. So just to rehash why we are here today, the purpose of this presentation was to identify the value of cloud-native best practices and explain that Kubernetes itself, while being a great starting place for cloud-native workloads, does not solve every problem. Fortunately, there are countless cloud services and projects, open source and closed, available to fill in the gaps, including plenty of things we didn't cover, such as service proxy, distributed databases and storage, stateful applications in general, messaging, streaming, the list goes on. The important thing to keep in mind is that this is a journey and there's no need to be overwhelmed. You can take each step as a bite-sized chunk and only move to the next phase when your team is comfortable to do so. If you'd like to deploy the application yourself, you can use the top two links that I have here. The next link is the one that I showed at the beginning, the fully deployed version of the application, and you're welcome to click it and poke around. The next link is some cloud native tutorials to follow. These go beyond the MuShop demo to some other basic activities. Also, I have included at the bottom the Oracle white paper that MuShop followed, the one that I mentioned at the top of the presentation, and also the cloud native trail map. At this time, we'll use the remaining time to answer some of your questions. It looks like there's been some coming over the Q&A chat. And if you haven't already, please feel free to ask any questions in the Q&A at any time. The first question is, at what point of our journey or for what kind of workload characteristics should we consider a service mesh? So from my perspective, application environments that would benefit most from using a mesh are self-contained microservice-based apps that are uniform in their deployment, have similar languages, although can be polyglot as long as they're instrumented correctly, and also similar in framework and API design. Because microservices are lightweight, ephemeral, and all have to interact very tightly together, it can be difficult to maintain reliable service-to-service connections at scale, which is what we talked about today. The value of a mesh decreases pretty rapidly if not all services of an application participate in it. If endpoints are too diverse, generated metrics are less comparable across the mesh, and observability suffers, and so do control functions. So I guess to recap that, meshes are great if you have relatively homogeneous microservice environments.
I think there's a question for me, which is, why did A10 Networks choose a cloud-native approach? Well, we wanted to offer a cloud-based controller which gave our customers all the virtues of a managed service. Beyond that, we also wanted to offer seemingly infinite storage for observability, be it metrics or logs, and then run machine learning services on top of that to predict service network impairments. So beyond infinite scale and volume, the idea was to offer an intelligent controller that added value in that it recognized patterns and could also be a prediction engine that would ensure the workloads are always served. We saw tremendous value and technical advantages in what OCI brought to the table. We also then started a lift and shift operation of a regression test on OCI. There's another question for me. Where did A10 Networks start its cloud native journey? Well, we had a classical on-prem DNA. So we made a conscious decision to run all our development, QA, and DevOps for this offering on OCI Cloud. So this way we could make the jump from a company with on-prem offerings to building a cloud-native product. We also use configuration management tools like Chef, Ansible for deployments. And again, to re-emphasize, with OCI's strong Terraform implementation, a lot of the heavy lifting was already done for us.